right, Ted, we are all set. And I'm super happy to have you as a speaker here, introducing Yaskawa's work on a ROS2 driver that runs natively on Yaskawa controllers. So, Ted Miller, the floor is yours. Let's go for the presentation. Great, thank you.
All right, thank you for having me. I'm here to introduce MotoROS2, which is our, as you said, our native node that runs on the robot controller. This work was done in collaboration with Delft University of Technology, specifically Heich van der Hoorn. It has been completely invaluable to this, and frankly, this wouldn't exist without his efforts. And we've built our node on top of the MotoROS platform, which is developed by Prosima, and they've done an excellent job of supporting us during the development. Special thank you to Pablo Garita. He's been very responsive and helpful and supportive during this effort. So the general overview is that we have what we believe to be the first native ROS2 node running on an industrial robot. So we are using the RCL libraries and the RCLC client library on top of that. We're using native ROS2 messages and actions and services, and this runs directly on the robot controller. So it actually starts up upon boot up of the controller. The node launches, is ready to go, and it's kind of always listening, if you will. We do route through a node on the PC called the MotoROS agent. I'll describe that a little bit more in the next slide. As far as compatibility, we're currently compatible with any robot that runs on the YRC-1000 platform, which is the current generation of our robot controller. It does also support the YRC-1000 Micro. We support up to 8 control groups. That can be a single robot arm, could be a linear track that moves the arm around, or it could be an external station that a part positioner that is outside of the robot's kinematic chain. And if you're familiar with the Motoman robot, we do have multiple teach-pendant options. Either one of those, it will work just fine. So as I mentioned before, we are running on the MotoROS platform, which was designed primarily for microcontrollers with extremely limited resources. On the Motoman, we're building this using the MotoPlus SDK, and what MotoPlus is it's not necessarily like so much an embedded platform such as like a microcontroller, but it does have limited resources, limited memory, limited CPU, different C standards, and MotoROS was helpful because it let us run on this constrained environment. There is an element that runs on the PC. It's kind of a bridge, if you will. The beauty of it is that there's no customization for the specifically for the Motoman. We didn't change anything. We didn't edit anything. If we add a new message, it doesn't matter. It just automatically takes care of all that for us. So MotoROS was a good solution for adapting the code to run in the MotoPlus environment so that we can control the robot in real time directly on the controller. For distribution, we just like our ROS1 implementation, the binaries will be available for download on GitHub. Anyone can download it. They can turn it on, enable the options on the robot controller without a technician, and no purchase is required. The source code for the driver will be open source, presented on GitHub, but to build it, it does require the MotoPlus SDK, which is a licensed product from Yaskawa. So if you want to use MotoROS2 as is, take it, run with it, have fun with it. If you need changes to customize it for your application, then there would require the SDK. It's a one-time purchase. The MicroROS code itself is also open source for the communication layer. However, we made some slight customizations specific to the MotoPlus to make it compatible with MotoPlus and the Motoman platform. As of right now, we're keeping those closed. They might be opened up later, not really sure. I mentioned earlier it's compatible with all robots that are on the YRC 1000 controller. So the collaborative robots, the standard industrial robots, Scaras, Deltas, dual arms, doesn't really matter. And if you have a robot that we haven't created a support package for, just make a request on GitHub, and we Yaskawa will support creating that. So as far as what the capabilities are of the ROS node, we have a table here listing some of them. I'm going to go through quickly and then describe it a little bit more. We get joint states of all the robots, the robot status. TF data is also available. We host motion control. We have two methods, one being a standard follow joint trajectory action, and the other being a service for queuing points. These tables are available in the slides if you'd like to read those over. But as far as our publishers, as I mentioned, we have joint states. That'll give you, it's a standard ROS2 message, of course. There's multiple topics available as far as if you have multiple robots connected to the same controller, you can get states for everything as all together or individually for each group by itself. Our robot status message will give you information, as far as whether there's an error, whether what motion mode you're using, whether motion is possible, and allows you just to monitor and control autonomously to be able to remotely deal with enabling the arm. TF data is optional. It's by default it is on. We are broadcasting, but if you don't want to use that because it might interfere with robot state publisher or something of that nature, we have a configuration option to turn it off. And all of these publish rates are also fully configurable. So if you need something to be broadcast a little more frequently or less frequently, that can be tuned to your application. The services that we're using currently, we have reading and writing of IO and registers. So you can reset and clear error states, assuming it's not a major error, of course. We've got setting the tool file number, which would affect all of your functional safety monitoring, and safety zones and whatnot. As I mentioned, there's two different modes of motion control. You can autonomously put the robot into the correct mode remotely, and I'll discuss those motion modes here. So we have two primary ways to control motion: the follow joint trajectory action server. So if you're using Move It and you want to plan out an entire path and send it to the robot controller, it just all comes as one big trajectory. Due to the resource constraints on the robot controller, we are limited to 200 points. So that's good. Like I said, if you have a predefined action in a destination, maybe palletizing or picking up parts out of a bin, each pick could be a pre-planned trajectory. The second option is if you don't necessarily have your entire trajectory planned out ahead of time, we have the Q trajectory point service, which is customized for the MotoROS2 interface. And this service allows you to submit motion points on the fly. So if you have sensor data that's adjusting where the robot needs to go, or if you just want to indefinitely keep streaming points because you don't want to be limited by the 200 point capacity, the Q trajectory point service is a good option for that. Additionally, there is say you do want to use the follow joint trajectory server, but you have more than 200 points, we have available a sample node that will do kind of like a translation for you. It'll convert a follow joint trajectory into the Q trajectory point. So if he has something like with 500 points in it, we can help you take care of that. So I mentioned there is a lot of configuration options available for the robot controller. We are not using a standard ROS parameter server at this time. One of the reasons for that is just MicroROS doesn't support necessarily string parameters, and but we allow you to customize things like the node name and the joint names if you want to change those, or namespace. There's a lot of different options available, and as I mentioned before, this currently starts up at boot time, so it's not like a managed lifecycle node, but rather it's just always on. It's at boot up time, it reads this configuration file, and that configures everything that you need to know in there. You can customize the QoS settings, so you can customize the publishing periods, the joint names, whether you want TF data or not. So there's a lot of options available that you can make it suit your application's needs. So we have had a few open issues, and that have caused us some trouble. For instance, the various DDS implementations out there, we are currently only compatible with the fast DDS from eProsima. So if you're using like say Galactic, with Galactic, the default DDS is actually Cyclone. And if you try to use that in conjunction with MotoROS2, it does not like that. So you can still use Galactic with MotoROS2. You do need to change everything to use fast DDS. We've also had some issues with QoS settings. So for instance, some applications expect like joint states to be best effort, while others expect them to be not best effort. I'm blanking on the term right now. I apologize. There's really no real good guidance for the entire ROS community as far as which messages should be in which QoS. So, but we allow you to customize that as needed. So as long as it matches, it works great. We've also had some issues with the changing of message definitions. For instance, with control messages when doing like the follow joint trajectory. The definition of the message in Foxy is different than Galactic and above because additional fields were added to the message type. And as I mentioned before, we've had size limitations as far as the size of the message itself. Being like, say, for instance, 200 points in the follow joint trajectory. Any of these issues here, when things don't talk right, it just kind of leads to a disappearing message where it's like you send something and nobody, the robot just doesn't respond because it doesn't actually end up seeing the message. So these are things to keep note of while working with MotoROS2, and we're working to try to make this better and improve upon the situation, but something to take note of. Mentioned before, it is YRC 1000 and YRC 1000 Micro with any robot model. We are looking at backporting this to the DX200 platform as well as potentially the FS100 platform. So it just kind of depends upon the need in the community as far as the feedback we get of what people want to see. We've currently in a closed beta program with 12 organizations. We expect everything to be publicly released sometime in the first quarter of 23. And then, that would be still in a beta state though, as we evaluate and we get feedback from additional users, make sure that we're hitting the things that they want us to hit as far as new features and or just how it operates. And then at this time, we don't know when it'll be officially released out of beta classification, but it just depends upon feedback from the community. So if there's something you want, a new feature you want, or it doesn't like how something is working, we want to hear about it. Post it up on GitHub discussions once it's public, and let us know. Based upon feedback from our beta users and additional internal folks, some of the things that we're kind of looking at developing as far as new features, and this is no particular order. Again, I mentioned legacy robot controller models, reading and writing controller variables. We currently have I/O and registers, but some people would like to also write variables so that they can do additional processes on the robot controller as far as controlling peripheral equipment. There have been requests for some sort of graphical user interface on the teach pendant. So again, we have both the standard industrial pendant as well as the smart pendant, more kind of like an iPad-like interface. So some sort of status monitor on there, or maybe be able to control the configuration settings from there, just to make that a little more user-friendly. One potential thing to look at is a ROS parameter support. So if we do end up doing more of like a managed lifecycle node and supporting actual parameter server for configuration, it'd be something to look at. Integration with ROS logging so that we can publish data to ROS out and it'd be logged along with everything else that's in the work cell. From a motion perspective, we've already got the 2 motion modes available. There's been some thought of having a kind of a high bandwidth real-time position streaming. So basically a route directly from ROS straight into the motion API of the robot controller, without any of our additional buffering or acceleration calculations or anything of that nature. So give you kind of maximum control at any moment. There's been requests for Cartesian interfaces. Currently, everything is done in joint angles, but so if you wanted to actually control the path of a TCP, it might be a little easier. For multi-robot applications, we currently require you to control all of the arms at the same time. So if each arm is doing something different, that has to be done in the motion planner itself, but then that planner has to submit the trajectory for all groups at once right now. So asynchronous control is something that some people have been expressed interest in, so they can do different things with different arms. Process control of peripheral equipment, as far as like welding or dispensing, things of that nature. Currently, the equipment would need to be controlled either from the ROS PC directly, or alternatively, we can make modifications to basically come in and out of ROS control mode. So you can tell the controller, okay, and now switch to native mode, now switch back to ROS mode. It's just clunky. So we would like to add some controls in there so that the users can directly command that equipment using a service call or something of that nature. And then lastly, the agentless operation, meaning without having that transparent bridge, although it's hardly cumbersome as it is today, it'd be nice just to have native true DDS capabilities on the robot controller. Thank you for your time. If anyone has any questions, I'd be happy to answer them.